Today we're going to focus on adding and subtracting radical expressions, which is going to be very, very similar to combining like terms, with the little catch that we do need to take a look at the radicals themselves, and before we try to combine anything, look at them and say, can I simplify you? So, first example, very straightforward. We have 3 root 7 plus 8 root 7. The radicals are identical. They're both root 7, and you can't simplify root 7. The only multiplication statement that makes 7 is 1 times 7. Nothing to do there. So this is basically saying I have 3 of this thing, and I get 8 more of this thing. Well, that must mean I have 11 of this thing being root 7. That's it. In the second example, we have 9 root y's, and we're subtracting a root y. Now, the common wrong answer here would be to say, well, that must be 9, because the root y minus the root y is just gone. That's not true. This is saying you have 9 of a thing, and you get rid of 1 copy of the thing. Well, that means you have 8 of the thing. In this case, the thing being root y's. In the third example, we have 12 root 2 minus 4 root 11. Those radicals are not identical. That doesn't mean we can't do the problem necessarily, but it does mean we need to try to simplify them if we can. So look at root 2. Well, the only way to make 2 is 2 times 1. No business there, no good, nothing. And the only way to make 11 is 11 times 1. So there are no perfect squares hiding here. We can't simplify these. So we can't add these, we can't subtract them. What can we do? All we can do is rewrite the problem. It is already a simplified expression. We can't do anything. In our fourth example, we have root 3d, we have a root 2d, and we have a root 3d. There are 2 of these 3 terms that will cooperate with each other, and they are the guys that both have the root 3d. If you have -8 of a thing, or you owe somebody $8 and then you get $10, presuming you pay them back, you now have $2. So -8 plus 10 of a thing means you have 2 of the thing, which is our root 3d. And the other radical expression, the 6 root 2d, it's a different type of radical. 3d and 2d are not the same thing, so we can't combine it with the other radicals. Root 12 plus root 27. Now your first instinct might be, we're done. They're not the same, we can't combine them. But this is a situation where you have to say, okay, 12 is 4 times 3, and 27 is 9 times 3. Both of these values, 12 and 27, have a perfect square hiding inside of them. In the first expression of root 4 times 3, the 4 can come out of the square root as its square root, which is 2, which leaves behind the root 3. In the second expression, the 9 comes out as a 3. Now we have like radicals. 2 root 3's plus 3 root 3's gives us a total of 5 root 3's. So we do have to consider that possibility. For example, 8 is 4 times 2. And 45, with a perfect square, specifically, is 9 times 5. Okay, remember, when I'm making these multiplication statements, I'm strictly looking for statements that involve one of our perfect square numbers. Okay, going back to the previous problem with the 12. I'm not going to use 6 times 2 as a multiplication statement right now, because neither 6 nor 2 are perfect. I only want to use a multiplication statement that involves one perfect square. So 8 is 4 times 2, makes sense, that's the only multiplication fact for 8. With 45, 9 times 5 is probably the first multiplication fact you think of. There's also 15 times 3, but we aren't going to use that one because 15 and 3 are regular numbers, they're not perfect squares. I want that 9. So now, this might be the first time we've seen this, but there's something that can simplify inside a radical that already has a value outside. So now what happens when that 4 comes out as a 2? It gets multiplied to the guy that was out front. And in the second expression, the 9 comes out as a 3. To simplify, we do need to multiply the 3 and the 2 that are both free and clear of their radical. So that's 6 root 2 plus 3 root 5. Now you can't actually combine these anymore. Root 2 and root 5, different radicals. But you must get the radicals to their simplest form for the answer to be correct. So if this problem came up on a quiz and you looked at that and decided you can't combine them because they're different radicals, you would get this problem completely wrong because you did not simplify the radicals. Okay? You must simplify the radicals, and then if you can combine, you will combine, but you must always simplify. So let's take a look here. We have 28x and 7x. 28 is 4 times 7x. That's nice. We like seeing that 7x because it's going to combine now with the other 7x. And remember, always choosing a multiplication fact that involves a perfect square. So 4 times 7, not 2 times 14. Also a multiplication fact that makes 28, but not a useful one to us right now. Now, as we saw above, when this 4 comes out of this radical as a 2, it will multiply with the 5 that was in front to become 10 root 7x minus 8 root 7x, and that's going to give us a final value of 2 root 7x. Last example for today. Those don't look like they agree at all, but I guarantee you there's a lot of simplifying we can do. So let's start with what makes 125? That's 25 times 5. What makes 20? Well, that's 4 times 5. And what makes 45? Well, that's 9 times 5. Look at that. All of the radicals separate into a perfect square times 5b. All those perfect squares are going to come out, and all those 5b's will be left behind, which means all 3 of these will then be amenable or agreeable to combining into a single answer. So our first term, the 25, comes out as a 5, so we get 5 root 5b. In the middle, the 4 comes out as a 2 and gets multiplied with the 3 that's already there to become 6 root 5b. And in our last expression, the 9 comes out as a 3, the 5b left behind. Combine like terms, which all of these are. 5 plus 6 is 11, minus the 3 on the end is 8 root 5b.